Welcome to Foundation Mathematics, Trigonometry, trig ratios, identities, and the angle addition formulae. The objectives for this session are to use trigonometry to find missing sides or angles, sketch trigonometric graphs and solve related problems, calculate the sine, cosine and tangent of any angle, know the exact trigonometric ratios for 30 degrees, 45 degrees and 60 degrees, know and use the relationships tan theta is identical to sine over cos and sine squared plus cos squared is identical to 1. Solve equations in sine, cos or tan. Solve equations, simplify expressions and prove simple identities which involved secant, cosecant and cotangent, and understand and use the addition and double angle formulae. First, let's review trigonometric ratios. In a right-angled triangle, three trigonometric functions are sine theta equals opposite over hypotenuse, cos theta equals adjacent over hypotenuse, and tan theta equals opposite over adjacent. Let's have a go at an example where we can apply these ratios. We are required to find the length of x to one decimal place in the given diagram. So as indicated, x is the opposite to the angle. 3.5 centimeters length is the adjacent to the angle. And therefore, when we solve, we're going to use tan theta equals opposite over adjacent. So substituting in the values gives us that tan 25 degrees equals x, which is the opposite, over 3.5 centimeters, which is the adjacent. And therefore, rearranging the equation gives us that x equals 3.5 times tan 25 degrees. And therefore, x is equal to 1.6. Let's now have a go at another example. We're required to find the size of theta to one decimal place. The side opposite theta is 2 centimeters, and the side adjacent to theta is 3.5 centimeters. So we're going to use the formula tan theta equals opposite over adjacent. And substituting in the values gives us tan theta remaining as it is, equals opposite, which is 2, over the adjacent, which is 3.5. And therefore theta equals tan inverse of 2 divided by 3.5. Which implies that theta equals 29.7 degrees. Let's now remind ourselves of the graphs of sine, cosine and tangent. The graphs of sine, cosine and tangent are periodic. This means they repeat themselves after a certain interval. So here's the graph of y equals sine x, and here's the graph of y equals cos x, and here's the graph of y equals tan x. We will now take a look at an example which will allow us to see how we can apply graphs to solving equations. So let's take a look at part A first. We are required to sketch the graph of y equals sine x in the interval x greater than or equal to 0 and less than or equal to 540 degrees. So let's solve this. The graph will look something like the one you can see on your screen now. In part B, we are required to find how many solutions there are to the equation sine x equals 0.7 in the range x between 0 and 540 degrees. So let's find 0.7, on the y-axis. This appears somewhere here. Now, at this point, there is one solution, as indicated. However, if we extend this line, we can see that there are actually 4 solutions in this range. The solutions are 44.4 degrees, 180 minus 44.4 degrees, 360 plus 44.4 degrees, and 540 minus 44.4 degrees. So this gives us the solutions as shown on your screen. We will now take a look at trigonometric functions sine, cos and tan in another context which will allow us to tackle a wider variety of problems. We will begin with the unit circle. Remember our unit circle with radius 1. For a point P on the unit circle such that OP makes an angle theta with a positive x-axis, we have that cos theta equals x, the x-coordinate of P, and sine theta equals y, the y-coordinate of P. We also have that tan theta equals y over x, the gradient of OP. Do note that we measure positive angles theta anti-clockwise from the positive x-axis. We are now going to use these definitions to find the sine, cosine and tangent of any angle theta. Let's consider this angle theta. As you can see, it is obtuse. However, the definitions remain the same. When theta is obtuse, cos theta, however, is negative because the x-coordinate of P is negative. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's solve part A first. We are required to find the value of sine 180 degrees. So let's solve this. Here's our unit circle. For theta equals 180 degrees, as shown in the diagram here, we have coordinates -1, 0. Therefore, from the definition we have that x equals cos 180 degrees, and from the diagram we have that this equals -1. We also have, similarly, y equals sine 180 degrees from the definition, and from the diagram we have that this equals 0. Therefore y is equal to 0. In particular, sine 180 degrees is equal to 0. We're now going to have a look at sine 270 degrees and cos 270 degrees. For theta equal to 270 degrees, we have the coordinates 0, -1, as shown. Therefore, x equals cos 270 degrees, which equals 0, and y equals sine 270 degrees, which equals -1, as shown. What about sine -90 degrees? For theta equal to -90 degrees, we have these coordinates. We're going clockwise this time as we're considering a negative angle. And so minus 90 degrees is actually equivalent to 270 degrees. So again, we're considering the point 0, minus 1. And so x equals cos minus 90 degrees, which equals 0, and y equals sine minus 90 degrees, which equals minus 1. We're now going to find the value of tan 45 degrees. But before we do this, let's explore the angle 45 degrees in the unit circle. The angle 45 degrees corresponds to the coordinates 1 over root 2, 1 over root 2. Let's take a look at this. Here's our unit circle. Here's x equals cos 45 degrees, and here's y equals sine 45 degrees. We can check the length of OP, and that indeed x squared plus y squared is equal to 1 over root 2 all squared plus 1 over root 2 all squared equals 1 by Pythagoras. So these are indeed the correct coordinates. So now we're ready to find the value of tan 45 degrees. For theta equals 45 degrees, remember we had the coordinates 1 over root 2, 1 over root 2. So x equals cos 45 degrees from the definition of x equals 1 over root 2 from the diagram. And y equals sine 45 degrees from the definition, and this equals 1 over root 2 from the diagram. So let's substitute the values of y and x. So here's y, and here's x. And of course, dividing one by the other gives us 1. So tan 45 degrees equals 1. Now let's take a look at some more theory. The 4 quadrants. Angles always lie in one of the 4 quadrants, even if they are greater than 360 degrees. So for example, 500 degrees equals 500 degrees minus 360 degrees, which is 140 degrees. Let's take a look at an illustration. Here are the x and y axes. And here's a point on the unit circle. And theta is the angle corresponding to this point on the unit circle. X is equal to cos theta, as we've defined it, and y equals sine theta, as we've defined that also. This is the first quadrant, and we begin at 0. Here's 90 degrees, and we go into the second quadrant, between 90 degrees and 180 degrees. After 180 degrees, we go into the third quadrant, and we stay in the third quadrant up to 270 degrees. And then the fourth quadrant is from 270 degrees to plus 360 degrees. And of course this is the same as 0 degrees. Now if we go the other way, we're at minus 90 degrees here in the fourth quadrant, so between 0 degrees and minus 90 degrees. And we're in the third quadrant from minus 90 degrees to minus 180 degrees. In the second quadrant, from minus 180 to minus 270. And finally, from minus 270 to minus 360, or 0 degrees, we're back in the first quadrant. So as you can see, x equals cos theta is positive, and y is also positive, and tan is also positive in the first quadrant. In the second quadrant, x is negative, y is positive, and since tan is defined as y over x, tan is negative. So sine is the only one out of the three which is positive. In the third quadrant, x is negative, y is negative, and of course, since tan is defined as y over x, tan is positive. So tan is the only one which is positive out of the three. And finally, in the fourth quadrant, we have that x is positive, y is negative, and therefore tan is also negative. So cos is the only one of the three which is positive. So here's a summary. One way of remembering this is cast, C-A-S-T. It is also known as the cast diagram. As shown. Using these rules, we can find sine, cos, and tan using the corresponding acute angle made with the x-axis. So let's take a look. Here's an illustration. Here are different ways in which we can see theta. 180 degrees minus theta has been highlighted, as you can see. Here, sine 180 minus theta is equal to sine theta, where theta is an acute angle. And tan 180 degrees minus theta equals minus tan theta, and cos 180 degrees minus theta is minus cos theta. However, if we're considering 180 degrees plus theta, we have that tan is positive. So tan 180 plus theta is equal to tan theta. However, the case for cos and sine is different. Cos 180 plus theta is minus cos theta, and similarly, sine 180 plus theta is minus sine theta. And finally, let's consider cos in the fourth quadrant. Cos 360 degrees minus theta, as highlighted, equals cos theta. However, sine and tan are both negative in this quadrant. So sine 360 degrees minus theta is minus sine theta, and tan 360 degrees minus theta is minus tan theta. Let's now take a look at an example using these laws. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. we are required to express sine minus 110 degrees in ratios of acute angles. Let's take a look at our cast diagram. Minus 110 degrees, as you can see from the diagram, is in the third quadrant. This makes an acute angle of 70 degrees with the x-axis. Now in this quadrant, only tan is positive, as you can see. And therefore, sine minus 110 degrees equals minus sine theta, or, in our example, minus sine 70 degrees. Trigonometric ratios of 30, 45 and 60 degrees can be found using triangles. Consider an equilateral triangle with side length 2 units, as shown. Notice that the angle ABC is 60 degrees, and each of the angles in the triangle is also 60 degrees. A perpendicular meets BC from A at D, as shown. So the length BD is now 1, because it's half of the side length. And the angle BAD is half of 60 degrees, which is of course 30 degrees, as shown. The height of the triangle is root 3, using Pythagoras. Pause the video and have a go at the example shown on the screen. When you are ready to view the solutions, press play. So let's solve part A first. We are required to find sine 30 degrees. We can use our triangle to do this. Since sine theta equals opposite over hypotenuse in a right-angled triangle, we have that sine 30 degrees equals 1 over 2. So here's theta, which is 30 degrees in our example. Here's the opposite, or the side opposite to theta, which is equal to 1, the length is 1, divided by the hypotenuse, whose length is 2. And so sine 30 degrees equals a half. Now let's solve part B. We are required to find cos 30 degrees, and we're going to use the same diagram as we did previously. This time, we're using the formula cos theta equals adjacent over hypotenuse. And again, in our example, we're considering 30 degrees as our angle, as shown. So theta equals 30 degrees. The adjacent is equal to root 3. And of course, the hypotenuse is equal to 2. So cos 30 degrees equals root 3 over 2. Now let's solve part C. We are required to find tan 30 degrees. We can use the formula for tan, opposite over adjacent. So therefore tan 30 degrees equals the length opposite, which is 1, divided by the adjacent, which is root 3. And so tan 30 degrees equals 1 over root 3. Now try finding sine, cos and tan of 60 degrees from this triangle yourself. Now that we have taken a look at the trig ratios of 30 degrees and 60 degrees, we can now examine the trig ratios of 45 degrees. Again, these can be found using triangles or a particular triangle. We're going to consider an isosceles right-angled triangle, PQR, like the one shown on your screen. PQ equals RQ equals 1 unit, as shown. and the length PR, the hypotenuse, is equal to root 2 from Pythagoras. Let's use this triangle to have a go at this example. Here we're required to find sine 45 degrees. So let's solve this. We are going to use the formula sine theta equals opposite over hypotenuse. So theta is equal to 45 degrees. The side opposite is equal to 1. And the hypotenuse has length root 2. And therefore sine 45 degrees equals 1 over root 2. So here's a summary of the trig ratios. For 30 degrees, for 60 degrees, and for 45 degrees. We are now going to use the information that we have about sine, cos and tan of 30, 45 and 60 degrees to help us solve another example. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We are required to find the exact value of sine minus 240 degrees. We're going to use the cast diagram to help us. Recall that the cast diagram tells us that if an angle lies in the first quadrant, then sine, cos and tan are all positive. If an angle lies in the second quadrant, only the sine is positive. If an angle lies in the third quadrant, then only tan is positive, and if an angle lies in the fourth quadrant, then cos is positive. Our angle is minus 240 degrees, so we go clockwise because it's negative. And this angle now lies in the second quadrant. Therefore, this is equivalent to 120 degrees. So sine minus 240 degrees is equal to sine 120 degrees. Since sine is positive, or the acute angle of sine is positive in the second quadrant, we have that sine 120 degrees is equal to sine 60 degrees. And of course, from the previous slides, we know that sine 60 degrees equals root 3 over 2. And therefore, sine minus 240 degrees is equal to root 3 over 2. Now, since we have that x squared plus y squared is equal to 1, we can substitute in the values for x and y in this equation to give us cos squared theta plus sine squared theta is identical to 1. We use the identity symbol instead of the equal symbol to show that this identity is true for all values of theta. Now, for all values of theta with cos theta not equal to 0, we have that tan theta is equal to y over x. Here's theta, here's y, and here's x. So substituting in y equals sine theta and x equals cos theta into this equation gives us that tan theta is equal to sine theta over cos theta. And in fact, tan theta is identical to sine theta over cos theta. Again, just as a reminder, the identity symbol shows that this identity is true for all values of theta. So we have these two key identities. Cos squared plus sine squared is identical to 1, and tan theta is identical to sine theta over cos theta. Now let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve this. Since we have for all values of theta, cos squared theta plus sine squared theta is identical to 1, we can simply replace theta by 4 theta, and the identity still holds. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solution. So in this example, given that cos theta equals minus 4 over 5 and that theta is reflex, we are required to find the value of sine theta. So let's solve this. Now since cos theta is negative, it must be in the second or third quadrant. When using your calculator to find this, it gives the incorrect result because the calculator gives you results between 0 degrees and 180 degrees. However, theta is reflex, so it must be in the quadrant number 3 or number 4. Let's remind ourselves of the cast diagram. In the first quadrant, sine, cos and tan are all positive. In the second quadrant, only sine is positive. In the third quadrant, only tan is positive. And in the fourth quadrant, only cos is positive. Now in the first part of the solution to example 3, we stated that because cos is negative, it must be in the second or third quadrant. However, we've also been told as part of the example statement that theta is reflex, and therefore it must be in the third or fourth quadrant. So therefore we can conclude that theta is actually in the third quadrant, because this is where both these conclusions overlap, as shown. And of course the little angle is 180 degrees minus theta. Using cos squared plus sine squared is identical to 1 gives us that sine squared equals 1 minus cos squared. And of course we can substitute cos theta equals minus 4 over 5 in this equation to give us that sine squared theta equals 3 over 5 all squared, which implies that sine theta equals plus or minus 3 over 5. Now, how do we know which of these it is? In the third quadrant, sine is negative. So therefore, we must take the negative value, and sine theta equals minus 3 over 5. We are now going to prove some more identities. Let's begin by recalling the reciprocal trigonometric functions. Sec equals 1 over cos, cosec equals 1 over sine, and cot equals 1 over tan. Remember that also we have that tan equals sine over cos implies that cot equals cos over sine. We can also use the identity sine squared plus cos squared is identical to 1 to prove other identities. We're going to do this in the first example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's consider part A first. We are required to prove that 1 plus tan squared x is identical to sec squared x. So let's solve this. We begin by dividing sine squared x plus cos squared x is identical to 1 by cos squared x. This gives us tan squared x, since tan x equals sine x over cos x, plus 1, since cos squared divided by cos squared is 1, is identical to sec squared x, since sec x equals 1 over cos x. And therefore we've proved the result. Now let's solve part B. We are required to prove that 1 plus cot squared x is identical to cosec squared x. So let's solve this. We're going to begin by dividing sine squared plus cos squared is identical to 1 by sine squared. As shown. Tidying up gives us 1, which is from, of course, sine squared divided by sine squared, plus cot squared x, since cot x equals cos x over sine x, is identical to cosec squared x, since cosec equals 1 over sine. And therefore we've proved the identity. Now let's take a look at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at this example. Given that tan A equals minus 8 over 15 and the angle A is a reflex angle, find the exact value of cosec A. So let's solve this. We're going to begin by using the identity 1 plus cot squared x equals or is identical to cosec squared x. To give us 1 plus cot squared A equals cosec squared A. Since tan A equals minus 8 over 15, we have that cot A equals minus 15 over 8. And so if we plug this into our equation, as shown, we have that 1 plus minus 15 over 8 all squared is equal to cosec squared A. And therefore, cosec squared A equals 1 plus 225 over 64, which equals 289 over 64. And so square rooting this gives us that cosec A equals plus or minus 17 over 8. In the cast diagram, we're only interested in the quadrants in which tan is negative, since tan A equals minus 8 over 15. And tan is negative in the second and fourth quadrants, where only sine is positive and only cos is positive. However, we're only interested in reflex angles, since that's what's stated in the exercise or the example, and therefore we're only actually interested in the fourth quadrant. And here we have that cosec A equals minus 17/8, since in the fourth quadrant sine is negative, and therefore, of course, 1/sine is negative also. We're now going to take a look at the addition formulae for sine, cos and tan. As shown here, we aren't going to prove them in this video, but a link to the proof can be found in the description below. However, we are going to apply these formulae to an example. Pause the video and have a go. Press play when you're ready to view the solution. So let's take a look at part A first. Given that sine A equals 4/5 and sine B equals 1/2, where the angles A and B are acute, calculate the exact value of sine A plus B. So let's solve this. We're trying to calculate sine A plus B, so we're going to use the sine A plus B formula. Here, we already know the values of sine A and sine B, but we're required to find cos B and cos A in order to plug these into the formula and find the value of sine A plus B. Using sine squared plus cos squared is identical to 1, we have that cos squared A equals 1 minus sine squared A. We're going to plug in the value of sine A as shown to give 1 minus 16/25, which is equal to 9/25. So cos squared A equals 9/25 implies cos A equals plus or minus 3/5. Now, since A is an acute angle, it lies in the first quadrant, and therefore cos A equals plus 3/5. So now we have the value of cos A. We're going to find cos B in a similar manner. Again, using the identity sine squared plus cos squared is identical to 1, we have that cos squared equals 1 minus sine squared. And so plugging in the value of sine B as shown gives us that cos squared B equals 1 minus 1/4, which is equal to 3/4. So cos squared B equals 3/4 implies that cos B equals plus or minus √3/2. Now, since B is an acute angle, it lies in the first quadrant, and therefore cos B equals √3/2. So now we have the values of cos A and cos B, as shown. We can now substitute the values into the formula for sine A plus B to give 4/5, since sine A equals 4/5, times √3/2, the value of cos B, plus 3/5, the value of cos A, times 1/2, which is the value of sine B. Tidying up this expression gives us 4√3/10 plus 3 over 10, which is equal to 4 root 3 plus 3 all over 10. Now let's take a look at part B. We're going to use the formula cos A minus B is identical to cos A cos B plus sine A sine B, in order to find the value of cos A minus B. From part A, we have that cos A equals 3 over 5 and cos B equals root 3 over 2. So if we substitute the values into this formula, we obtain 3 over 5 times root 3 over 2 minus 4 over 5 times a half, to give us 3 root 3 over 10 minus 4 over 10, which is equal to 3 root 3 minus 4 all over 10. And now for part C. Given that sine A equals 4 over 5 and sine B equals 1 over 2, where the angles A and B are acute, calculate the exact value of sec A minus B. So let's solve this. We know that sec A minus B is identical to 1 over cos A minus B. Also, from part A, we have that cos A minus B equals 3 root 3 minus 4 all over 10. So plugging this into the formula for sec A minus B gives us this expression here, which when tidied up is equal to 10 over 3 root 3 minus 4. We are now going to take a look at the double angle formulae. We're going to prove the double angle formulae by using the addition formulae. Let's consider sine A plus B first. If we let A equal B in the formula for sine, we obtain sine A plus A is identical to sine A cos A plus cos A sine A. And therefore, if we tidy up, we obtain sine 2A is identical to 2 sine A cos A. And this is our first double angle formula. Let's now take a look at the addition formula for cos. If we let A equal B in the formula for cos, we obtain cos A plus A is identical to cos A minus sine A sine A. And so if we tidy up, we obtain cos 2A is identical to cos squared A minus sine squared A. And we can rearrange this to be written as cos squared A minus 1 minus cos squared A. We've of course replaced sine squared A by 1 minus cos squared A. And this gives us 2 cos squared A minus 1. So cos 2A is also identical to 2 cos squared A minus 1. Similarly, we can write cos 2A as being identical to 1 minus 2 sine squared A. Now let's take a look at the formula for tan. Again, if we let a equal b in the formula for tan, we obtain tan 2a equals tan a plus tan a all over 1 minus tan a, which is identical to 2 tan a all over 1 minus tan squared a. And this is the double angle formula for tan. So here are the double angle formulae. We're going to apply one of these formulae to an example. Pause the video and have a go. Press play when you're ready to view the solution. So in this example, we are required to use one of the double angle formulae to write cos squared 22.5 degrees minus sine squared 22.5 degrees as a single trigonometric ratio. So let's solve this. The formula which will best fit this example is cos, since we have cos 2a is identical to cos squared a minus sine squared a, and therefore we can apply this to this example. Tidying up gives us that cos 2 times 22.5 degrees is equal to cos 45 degrees. And therefore we've expressed cos squared 22.5 degrees minus sine squared 22.5 degrees as a single trigonometric ratio. This brings us to the end of this session. If you have understood its contents, you should be able to use trigonometry to find missing sides or angles, sketch trigonometric graphs and solve related problems, calculate sine, cos and tan of any angle, know the exact trigonometric ratios for 30 degrees, 45 degrees and 60 degrees, know and use the relationships tan is identical to sine over cos and sine squared plus cos squared is identical to 1. Solve equations in sine, cos or tan, and solve equations, simplify expressions and prove simple identities which involve secant, cosecant and cotangent. You should also be able to understand and use the addition and double angle formulae. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.